Tonight, as you settle into stillness, let us begin a journey outward from where you rest. We will travel through scales of distance so vast that numbers lose meaning and imagination strains to comprehend. But we will go slowly, peacefully, allowing each scale to settle before moving to the next, building an understanding of cosmic vastness that can accompany you gently into sleep. As your breath slows and deepens, picture yourself lying in your room. The space is familiar, a few meters wide, a few meters long, perhaps 3 meters from floor to ceiling. This is human scale, the size range where your intuition works perfectly, where you can estimate distances by eye, where everything feels comprehensible and manageable. Now expand your view to include your building, your street, your neighborhood. At this scale, hundreds of meters, perhaps a kilometer, you still understand size intuitively. You've walked these distances countless times. You know how long it takes to traverse them, how they appear from different angles, how they connect to each other. This is still your territory, comprehensible through direct experience. Expand further to encompass your city or town. Now we're dealing with tens of kilometers, distances that take significant time to cross even in vehicles, areas too large to see all at once from ground level, but small enough that you've probably explored most parts at some time. The scale is stretching beyond direct experience, but remains graspable through mental maps built from many journeys. Picture, as sleep approaches, your entire country or region, hundreds or thousands of kilometers across. At this scale, direct experience becomes fragmented. You've perhaps visited some locations, but not others. You understand the shape intellectually, from maps, from flights where you've seen the landscape compressed by altitude, but you cannot hold it all in direct perception simultaneously. Your intuition is beginning to fail. Numbers are starting to replace felt experience. Now expand to encompass the entire Earth. Our planet is about 12,742 kilometers in diameter, 40,075 kilometers around at the equator. These numbers are easy to say, but impossible to truly feel. No human has ever seen all of Earth simultaneously except as photographs from space. The planet is too large for direct perception, too vast for intuitive understanding. We represent it with globes and maps, abstractions that let us think about it without experiencing it. Yet Earth, as you rest in its gravity, feeling its solid surface beneath you, is tiny compared to what lies beyond. It is our home, seemingly large because it contains all human experience, but in cosmic terms, it is a speck, less than a grain of sand on a cosmic beach. Tonight, we will journey outward from this speck, discovering scales that make Earth seem vanishingly small, yet somehow finding peace in that smallness rather than insignificance. From Earth's surface, the Moon is the nearest celestial object, an average of 384,400 kilometers away. This distance, about 30 Earth diameters, is the farthest humans have traveled. The Apollo missions of the 1960s and 70s took 3 days to cover this distance, the fastest humans have ever journeyed. Light traveling at 299,792 kilometers per second takes 1.3 seconds to cross from Earth to Moon. This is already a distance that challenges comprehension. If you could drive to the Moon at highway speed, 100 kilometers per hour, the journey would take 160 days of continuous driving. If you walked at 5 kilometers per hour, it would take over 8 years without stopping. The moon looks close in our skies, familiar and accessible. Yet it represents a gulf of emptiness far wider than any ocean, crossed by only a handful of humans across all of history. As you drift towards sleep, consider the Sun, our star, the gravitational anchor of our solar system, source of the light and warmth that makes Earth habitable. The Sun lies about 150 million kilometers from Earth, a distance called 1 astronomical unit, an AU, which becomes our measuring stick for the solar system. Light from the Sun takes 8 minutes and 20 seconds to reach Earth. When you see the Sun, you see it as it was 8 minutes ago. If the Moon's distance challenges intuition, the Sun's distance obliterates it. At highway speed, driving to the Sun would take 171 years. Walking would take 3,400 years, longer than recorded human history. Yet you see the Sun daily, a bright disk in the sky, appearing close and immediate. The cosmos deceives our senses, presenting vast distances as apparent nearness, hiding true scale behind visual simplicity. The solar system extends far beyond the Sun. Mercury, the innermost planet, orbits at 0.39 astronomical units, about 58 million kilometers. Venus at 0.72 astronomical units, Earth at 1 astronomical unit, Mars at 1.52 astronomical units. These inner planets occupy a relatively compact region around the Sun, all within about 230 million kilometers. Then comes the asteroid belt, a region of rocky debris between 2.2 and 3.2 astronomical units, remnants of planet formation that never coalesced into a world. Beyond the asteroid belt, distances expand dramatically. Jupiter orbits at 5.2 astronomical units, 778 million kilometers from the Sun. Saturn at 9.5 astronomical units. Uranus at 19.2 astronomical units. Neptune at 30 astronomical units, about 4.5 billion kilometers, 30 times Earth's distance from the Sun. Light from the Sun takes 4 hours to reach Neptune. If you stood on Neptune and watched the Sun set, it would have actually set 4 hours earlier. The light showing you sunset left the Sun's surface when you were still at lunch. Picture yourself, as sleep draws closer, seeing the solar system from above, all the planets in their orbits around the Sun. Even at this scale, where we compress billions of kilometers into a mental image, the planets occupy mostly empty space, tiny dots separated by vast distances, held in gravitational embrace by the Sun, yet immensely isolated from each other by the vacuum between. But Neptune is not the edge of our solar system. Beyond Neptune lies the Kuiper Belt, a region of icy objects extending from 30 to 50 astronomical units, containing dwarf planets like Pluto and hundreds of thousands of smaller bodies. Beyond that, even more distant, lies the Oort cloud, a spherical shell of icy objects surrounding the entire solar system, extending from 2,000 to 100,000 AU, about 1/4 to halfway to the nearest star. The Oort cloud marks the edge of the Sun's gravitational dominance, the farthest reach of our solar system's influence. An object in the outer Oort cloud orbits the Sun once every several million years. Light from the Sun takes about a year and a half to reach the outer edge of the Oort cloud. This is already approaching the distance to the nearest stars, and we haven't even left our own solar system yet. As you rest, feeling Earth's familiar gravity, breathing Earth's atmosphere, warmed by light that left the Sun 8 minutes ago. Consider that we've described only our local cosmic neighborhood. One star and its retinue of planets and smaller objects, occupying a bubble about 2 light-years across. And even this local region is so vast that humans have explored only the tiniest fraction, have sent spacecraft only to the innermost planets, have measured distances only approximately to the outermost regions. Tonight, we're just beginning our journey outward. We've stretched our intuition past breaking, moved beyond scales where numbers have experiential meaning, but we've barely left home. The true vastness of the universe lies ahead, measured not in millions or billions of kilometers, but in light-years, parsecs and megaparsecs, units invented specifically because familiar distance measures become absurdly inadequate for cosmic scales. Rest now as we pause at the edge of the solar system, preparing for the vast leap to the nearest stars. Let the distances already covered settle into your thoughts. Earth to moon to sun to planets to the outer reaches where the sun's influence fades. Each scale larger than the last, each one harder to grasp, each one revealing that what seemed vast is actually tiny compared to what lies beyond. This is the nature of cosmic scale. Each expansion reveals new expanses. Each horizon opens onto larger vistas. Each measurement shows that the universe is bigger than we imagined. The gulf between stars, crossing interstellar space. As your muscles relax and your mind drifts into receptive calm, we leave the solar system behind and venture into the gulf between stars. Distances so vast that kilometers become meaningless, and we must measure in light-years the distance light travels in 1 year, about 9.46 trillion kilometers. Picture, as you rest, the nearest star to our Sun, Proxima Centauri, a small red dwarf in the Alpha Centauri system, lying 4.24 light-years away. Light from Proxima Centauri takes 4.24 years to reach Earth. When you look toward it in the sky, you see it as it was over 4 years ago. If it exploded today, we wouldn't know for more than 4 years. The gap between stars imposes a delay on information, a cosmic speed limit that means events and their observations are always separated by time. To grasp this distance, consider our fastest spacecraft. Voyager 1, launched in 1977, is currently the most distant human-made object, traveling at about 17 kilometers per second relative to the Sun, roughly 61,000 kilometers per hour. After more than 45 years of travel, Voyager 1 is about 24 billion kilometers from Earth, roughly 160 astronomical units, having just begun to exit the heliosphere, the bubble of charged particles surrounding our solar system. At Voyager's speed, reaching Proxima Centauri would take over 73,000 years. The entirety of recorded human history would pass more than 7 times over during the journey. Civilizations would rise and fall. Languages would evolve beyond recognition. The descendants of the people who launched the spacecraft would have no cultural memory of the mission's beginning. Yet Proxima Centauri is our nearest neighbor, the closest possible interstellar destination. As sleep approaches, consider what this means. The stars you see at night, appearing as a canopy of lights, are separated by distances that make solar system scales seem trivial. The Sun's nearest neighbor is 275,000 times farther than Earth is from the Sun. If you built a scale model where Earth and Sun were 1 meter apart, Proxima Centauri would be 275 kilometers away. The space between stars is emptier, vaster, more profoundly isolated than the space between planets. Within 10 light-years of the Sun lie only 14 known star systems, most of them dim red dwarfs, visible only with telescopes. Within 50 light-years, there are roughly 2,000 star systems, still remarkably sparse. The average distance between stars in our region of the galaxy is about 5 light-years. Stars are not scattered uniformly, but clustered in some regions and sparse in others. Yet overall, the galaxy is mostly empty space, with stars as rare islands separated by vast gulfs. Picture the galaxy from outside as you drift towards sleep. The Milky Way is a barred spiral galaxy about 100,000 light-years in diameter and 1,000 light-years thick at the disk. More at the central bulge. It contains between 100 and 400 billion stars. Estimates vary because much of the galaxy is hidden behind dust clouds and we can only observe it from inside. These billions of stars occupy a volume so vast that despite their enormous number, they are separated by light-years of mostly empty space. Our Sun lies about 27,000 light-years from the galactic center, in a minor spiral arm called the Orion Spur, orbiting the galactic core at about 230 kilometers per second. At this speed, the Sun completes one galactic orbit, one cosmic year, every 225 to 250 million years. The last time our solar system was at its current position in the galaxy, dinosaurs had not yet evolved. The Sun has completed about 20 orbits since its formation 4.6 billion years ago. The galactic center, 27,000 light-years away, hosts a supermassive black hole called Sagittarius, a star, with a mass of about 4 million times the Sun's mass. Light from the galactic center takes 27,000 years to reach us. The center we observe is ancient. We see it as it was when Earth was in an ice age and humans were anatomically modern but had not yet developed agriculture. The galaxy we observe exists in the past, each star seen as it was when its light began the journey, the more distant ones seen progressively farther back in time. As you rest, consider traveling across the galaxy at light speed, the fastest possible velocity, the speed at which information propagates. Even at this ultimate speed, crossing from our position to the far side of the galaxy would take 100,000 years. Crossing just to a star halfway toward the galactic center would take 13,500 years. The galaxy, though it appears as a band across the night sky, is vast beyond human scales. A collection of billions of stars separated by distances measured in light-years, all slowly orbiting a common center in a rotation that takes hundreds of millions of years. The Milky Way is not isolated. It's part of a small cluster called the Local Group, containing about 80 galaxies within a region roughly 10 million light-years across. Our nearest large galactic neighbor is Andromeda, the Andromeda Galaxy, a spiral galaxy similar to but slightly larger than the Milky Way, lying about 2.5 million light-years away. Light from Andromeda takes 2.5 million years to reach us. When you see Andromeda in the night sky, visible as a faint smudge to the naked eye, you see it as it was 2.5 million years ago, when early human ancestors like Homo habilis were just beginning to use simple stone tools. The light showing you Andromeda's current appearance left that galaxy when Earth was in a different ice age, when different species walked the planet, when human history was unimaginably distant in the future. Picture yourself as sleep draws nearer, seeing the local group from outside. Two large spiral galaxies, Milky Way and Andromeda. One smaller irregular galaxy, Triangulum, and dozens of dwarf galaxies scattered across 10 million light-years of space. The group is gravitationally bound, meaning all these galaxies orbit their common center of mass, drawn together by gravity despite the vast distances separating them. Andromeda and the Milky Way are actually approaching each other at about 110 kilometers per second. In approximately 4.5 billion years, they will collide. Though collide is misleading because stars are so widely separated that actual stellar collisions will be rare. The galaxies will pass through each other, gravitationally disrupting their structures, likely merging over hundreds of millions of years into a single, larger elliptical galaxy. This is the distant future of our galactic neighborhood, a slow-motion cosmic dance spanning billions of years. Beyond the local group, other galaxy groups and clusters populate the cosmos. The nearest large cluster is the Virgo cluster, about 65 million light-years away, containing roughly 1,500 galaxies. The local group, Virgo cluster, and other nearby groups and clusters form the Virgo supercluster, a larger structure about 110 million light-years across, containing tens of thousands of galaxies. As you drift toward unconsciousness, consider that we've now expanded from Earth through the solar system, across interstellar distances to nearby stars, across the Milky Way to distant stars within our galaxy, across intergalactic space to nearby galaxies, and finally to clusters and superclusters containing thousands of galaxies. And we're still only describing our local cosmic neighborhood. The observable universe extends much, much farther. The distances between galaxies are vast, even compared to the distances between stars. If you scaled the galaxy down so the distance from Earth to the Sun was 1 centimeter, the Milky Way would be about 2 kilometers across, and Andromeda would be about 50 kilometers away. At this scale, galaxies become like islands, separated by oceans of empty space, each containing billions of stars, yet each isolated from neighbors by distances so vast that light takes millions of years to cross them. Tonight, as sleep claims you, rest in the knowledge that the universe contains structure at every scale. Stars separated by light years within galaxies. Galaxies separated by millions of light years within groups and clusters. Clusters separated by even greater distances in the larger cosmic web. Each scale is vast compared to the previous one, each expansion revealing that what seemed enormous is actually small compared to the next level. The universe is built in layers of increasing scale, each one challenging comprehension, each one revealing that our intuitive sense of size and distance applies only to the tiniest, most local region of existence. The observable universe, horizons of light and time. As your breathing settles into the rhythm of approaching sleep, we reach the largest scale comprehensible to current science. The observable universe, the region from which light has had time to reach us since the Big Bang. This is not necessarily the entire universe, which may be infinite, but it is the portion we can observe, limited not by technology, but by the finite age of the universe and the finite speed of light. Picture, as you rest, the concept of cosmic horizons. Light travels at finite speed, about 300,000 kilometers per second. Nothing can travel faster. Information, including light, takes time to cross distances. The farther something is, the longer light from it takes to reach us, and therefore the farther back in time we see it. When we observe distant objects, we're not seeing them as they are now, but as they were when the light we're receiving left them. The universe is about 13.8 billion years old, having begun in the Big Bang. You might think, therefore, that the observable universe has a radius of 13.8 billion light-years, the distance light could have travelled since the beginning. But the universe has been expanding during that time, stretching space itself, carrying distant objects farther away even as their light travels toward us. Because of this expansion, the observable universe is actually much larger than 13.8 billion light-years in radius. The current size is about 46.5 billion light-years in radius, meaning the observable universe is a sphere about 93 billion light-years in diameter, centered on Earth. This is the cosmic horizon, the edge of what we can observe, beyond which light has not had time to reach us since the Big Bang. As sleep draws nearer, consider what this means. There are objects whose light is only now reaching us after travelling for most of cosmic history. The light left those objects when they were much closer, but during the 13+ billion years the light travelled. The expansion of space carried the objects farther away, so they're now about 46 billion light-years distant. We see them as they were shortly after the Big Bang, but they've evolved significantly since then. If they still exist, they look nothing like what we observe. The observable universe contains an estimated 2 trillion galaxies, each containing tens or hundreds of billions of stars. If we estimate conservatively that the average galaxy contains 100 billion stars, the observable universe contains roughly 200 billion trillion, 2 times 10 to the 23rd power stars. This number is so vast that it exceeds the number of grains of sand on all Earth's beaches. The universe contains more stars than all the grains of sand, all the drops of water, all the atoms readily accessible in your everyday experience. Yet even this vast number is a lower limit counting only the observable universe. The entire universe, beyond what we can see, may be infinite. The observable universe is just the portion within our cosmic horizon, the region from which light has reached us. Beyond that horizon lies more universe that we cannot see because light from it hasn't had time to arrive. That unseen region may extend infinitely, containing infinite stars, infinite galaxies, infinite variations of matter and energy. Picture yourself as you drift towards sleep, as a single conscious being on a planet orbiting one star among 200 billion trillion, in one galaxy among 2 trillion, in a universe that may be infinite. Your entire existence occupies an almost inconceivably tiny fraction of space and time. Earth is a speck within the solar system. The solar system is a speck within the galaxy. The galaxy is a speck within the local group. The local group is a speck within the Virgo supercluster. And the observable universe extends thousands of times farther than the Virgo supercluster. The expansion of the universe is accelerating, driven by dark energy, a mysterious component that comprises about 68% of the universe's energy density. This acceleration means that extremely distant galaxies are receding from us faster than light, not because they're moving through space faster than light, which is impossible, but because space itself is expanding so rapidly that the distance between us and them increases faster than light can cross it. Galaxies currently beyond a certain distance, the cosmic event horizon, roughly 16 billion light-years away, are receding so fast that light leaving them now will never reach us. Even though they exist, even though they're part of the universe we share, we will never see them. They've passed beyond our cosmic horizon forever, isolated by expanding space. The observable universe, in fact, is shrinking in terms of which galaxies we can potentially observe, even as the physical universe continues expanding. As you rest, consider the cosmic microwave background, the afterglow of the Big Bang, visible in all directions as faint microwave radiation. This light was emitted about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. The cosmic microwave background represents the most distant thing we can observe, not individual stars or galaxies, but the hot, dense state of the entire early universe. The objects that emitted the cosmic microwave background are now about 46 billion light-years away due to expansion. We see them as they were 13.8 billion years ago, shortly after the Big Bang, but they've been receding from us all this time and are now far beyond the distance light traveled to reach us. If we could somehow see them as they are now, they would be mature galaxies, evolved and aged, nothing like the hot plasma they were when they emitted the light we're receiving. The large-scale structure of the universe resembles a cosmic web. Galaxies clustered into groups and clusters, clusters connected by filaments, and walls containing chains of galaxies, with vast voids between containing few galaxies. This structure formed from tiny density fluctuations in the early universe, amplified by gravity over billions of years, creating the distribution we observe today. The cosmic web extends throughout the observable universe, with structure at all scales. Galaxies within groups, groups within clusters, clusters along filaments, filaments defining voids. The largest structures, superclusters and filaments, extend hundreds of millions of light-years. Yet even these vast structures are small compared to the observable universe's overall size. As sleep approaches, picture the observable universe as a sphere 93 billion light-years across, filled with a cosmic web of galaxies, each galaxy containing billions of stars, each star potentially hosting planets. All of this structure emerging from an initial state of nearly perfect uniformity 13.8 billion years ago, shaped by gravity, cosmic expansion, dark matter, and dark energy into the complex, structured universe we observe. Consider that we see the universe in time as well as space. Nearby galaxies appear as they were millions of years ago. Distant galaxies appear as they were billions of years ago. The cosmic microwave background shows us the universe as it was 380,000 years after the Big Bang. When we observe the universe, we're seeing its history, watching its evolution, observing not a single moment, but a sequence of moments stretching from the present back toward the beginning. The observable universe is not just vast in space, but deep in time. Every observation is also a look backward, a glimpse of the past. The night sky is a time machine, showing us the cosmos at various stages of its development. Nearby stars as they were years ago, distant stars as they were centuries or millennia ago, other galaxies as they were millions or billions of years ago. We observe cosmic history laid out spatially, with distance translating to time, each light year of distance representing 1 year of looking back. As you drift into unconsciousness, let the scale of the observable universe settle gently into your thoughts. 93 billion light-years in diameter, 2 trillion galaxies, 200 billion trillion stars, cosmic structures hundreds of millions of light-years across, a history stretching 13.8 billion years into the past, an expansion that continues, accelerating, carrying distant galaxies beyond our ability to ever observe them. All of this arising from an initial state of extraordinary density and temperature, evolving through cosmic time into the structured, vast, ancient universe we observe today. The observable universe is the largest structure we can discuss scientifically, the ultimate context for all existence we can measure. Yet it may be just a tiny fraction of the total universe, possibly an infinitesimal speck within an infinite cosmos, or perhaps one of many universes in a larger multiverse. We cannot know. The cosmic horizon limits our observations. Beyond what we can see lies mystery, more universe that may be similar to what we observe, or may be radically different, or may not exist at all. The observable universe is simultaneously the largest thing we know and possibly a vanishingly small sample of reality. Perspective. Finding peace in cosmic scale. As your body settles into deepening rest, let us return from the cosmic distances we've traveled and consider what these scales mean. How cosmic vastness relates to human existence. How unimaginable distances affect our understanding of reality. And how contemplating the universe's size can bring not anxiety but peace. Picture, as you drift toward sleep, the scales we've traversed tonight. From your room to your planet. From Earth to the Moon, 384,000 kilometers. From Earth to the Sun, 150 million kilometers. Across the solar system to Neptune, 4.5 billion kilometers. To the edge of the Oort cloud, nearly 2 light-years. To the nearest star, Proxima Centauri, 4.24 light-years. Across the galaxy, 100,000 light-years. To Andromeda, 2.5 million light-years. To the edges of the observable universe, 46.5 billion light-years. Each expansion revealed that what seemed vast was actually tiny compared to the next scale. Each number stretched intuition farther beyond breaking. Yet somehow, in contemplating these distances, in recognizing how truly vast the universe is, and how truly tiny our place in it, something profound can emerge. Not insignificance, but perspective. Not anxiety, but calm. Not despair, but wonder. You are small. Earth is small. The solar system is small. Even our galaxy is small within the cosmic context. Everything you've experienced, everything humans have experienced collectively, every war and peace, every triumph and tragedy, every love and loss, all of it has occurred on one planet, orbiting one star, among billions in one galaxy, among trillions in a possibly infinite universe. As you rest, consider that this smallness need not mean meaninglessness. A poem is not diminished by being shorter than an encyclopedia. A flower is not less beautiful because the forest is vast. The love you feel for another person is not reduced by the existence of billions of other people. Value is not determined by size. Meaning is not proportional to scale. Your life matters to you with absolute intensity. Your experiences fill your consciousness completely. Your joys and sorrows are vivid and immediate, regardless of cosmic context. The universe's vastness doesn't diminish your experience. It provides a context that can make your experience feel even more precious because it is unique, fleeting, improbable against cosmic odds. Consider the unlikelihood of your existence. The universe could contain only hydrogen and helium, the simplest elements created in the Big Bang. But stars forged heavier elements in their cores, exploded as supernovas, scattered those elements through space. Second-generation stars formed from enriched material, hosted planets, created conditions where chemistry became complex. On at least one planet, possibly many, chemistry became biology. Self-replicating molecules appeared, evolution began, life diversified, complexified, eventually producing consciousness, matter that can contemplate itself. Atoms arranged in patterns so intricate they become aware, universal stuff, organized into structures capable of wondering about the universe. You are the universe experiencing itself. The atoms in your body were forged in stellar cores, scattered by supernovas, condensed into planets, organized by evolution into living systems, and finally arranged into the specific pattern that is you, conscious, aware, capable of understanding the cosmic context of your existence. This is not common. Most matter is in stars or gas clouds or black holes, unconscious, unaware. The fraction of universal matter organized into conscious beings is vanishingly small, which makes consciousness extraordinarily precious. As sleep draws very close, consider that contemplating cosmic scale can be a meditation on perspective itself. When daily concerns feel overwhelming, when problems seem insurmountable, cosmic perspective reminds you that the universe is vast, time is long, and your current troubles occupy a tiny sliver of space and time. They are real and important to you, but they are not permanent or universe-defining. This perspective doesn't solve problems but can create emotional space around them, reducing their ability to dominate consciousness. The universe is also teaching us humility. For most of human history, we imagined Earth at the center of everything. Special, unique, the focus of cosmic attention. Each scientific advance has decentered us. Earth orbits the Sun, not vice versa. The Sun is ordinary, not special. The Milky Way is one galaxy among trillions. Even our observable universe may be one among infinite regions or universes. Yet, this decentering has revealed something wonderful. The universe operates by comprehensible laws. The same physics governing Earth's surface applies throughout the cosmos. Light from distant galaxies follows the same principles as light from your lamp. Gravity works identically here and in galaxy clusters billions of light years away. The universe is vast, but not arbitrary. It follows rules, and those rules can be understood by creatures like us. Tiny, brief, yet capable of comprehending cosmic scales and fundamental laws. Picture yourself one last time as you drift toward unconsciousness, a conscious being on a planet orbiting a star in a galaxy containing billions of stars, in a universe containing trillions of galaxies, possibly infinite in extent, certainly vast beyond human scale, ancient beyond human history, structured by laws that you can partially understand despite your tiny size and brief existence. This is simultaneously humbling and empowering. Humbling because you are small. Empowering because, despite being small, you can contemplate vastness, understand cosmic scales, grasp principles governing reality at all levels. Your physical size is tiny, but your intellectual reach extends across the observable universe. Your lifespan is brief, but your understanding spans from the Big Bang to the distant future. You are small, but capable of comprehending immensity. As sleep finally claims you, rest in this perspective. The universe is vast, you are tiny. And both things are true without contradiction, without diminishing either cosmic grandeur or personal significance. The stars continue their ancient motions light years away. Galaxies continue rotating and colliding millions of light years distant. The universe continues expanding, carrying cosmic horizons ever farther from our observational reach. And you rest here, breathing quietly, existing peacefully. A tiny part of the vast whole, brief but real, small but conscious. Limited in size, but unlimited in curiosity. A temporary pattern of matter that can wonder about its place in the cosmic scale, that can feel awe at immensity, that can find peace in perspective, that can rest, knowing you are part of something incomprehensibly large, yet fundamentally comprehensible. A universe that follows laws, that can be studied, that reveals its secrets to careful observation and patient thought. Numbers and light, understanding, distance through time. As your muscles fully relax and sleep draws very near, let us consider one more aspect of cosmic distance that makes it both comprehensible and profound. The relationship between distance and time, how every cosmic distance also represents a journey backward in time, making astronomy not just the study of space, but the study of history. Picture, as you rest, the simple fact that light travels at finite speed. Nothing is instantaneous across distance. When you see something, you see it not as it is now, but as it was when light left it. For nearby objects, this delay is negligible, microseconds or milliseconds. But across cosmic distances, the delay becomes significant, then dominant, then the defining feature of observation. The moon, as you drift towards sleep, appears as it was 1.3 seconds ago. By the time you see the moon, it has moved slightly from where you observe it, though the difference is far too small for human perception. The sun appears as it was 8 minutes and 20 seconds ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. The light showing us the sun would continue arriving for that duration, and only then would darkness fall. Jupiter, depending on its position in its orbit relative to Earth, appears as it was between 32 and 52 minutes ago. When you observe Jupiter through a telescope, you see not its current configuration, but its past configuration. And if you watch carefully over time, you notice that moons appear in slightly different positions than predictions based on current orbital calculations suggest they should, because you're seeing where the moons were in the past, not where they are now. Neptune appears as it was about 4 hours ago. Pluto and other Kuiper Belt objects appear as they were 4 to 7 hours ago. Objects in the Oort cloud, if we could observe them directly, would appear as they were months or years ago. Already, within our solar system, we're looking not just across space, but back through time, observing history rather than present. The nearest star, Proxima Centauri, appears as it was 4.24 years ago. Any explosion, any planetary transit, any stellar flare that occurs today won't be visible from Earth until 2029 or later. If intelligent life existed on planets around Proxima Centauri and sent us a message today, we would receive it in 2029. If we replied immediately, they would receive our response in 2033, an 8.5-year round-trip time for conversation. Interstellar communication is necessarily delayed, with intervals of years between messages, making real-time dialogue impossible. As you drift into unconsciousness, consider the implications for observing distant galaxies. Andromeda appears as it was 2.5 million years ago. The light showing you Andromeda left that galaxy when early humans were just beginning to use tools, before Homo sapiens existed, when Earth was in a different ice age. You cannot see Andromeda as it is now. You can only see its past, and its now is forever inaccessible until 2.5 million years from now, when light showing today's Andromeda will finally reach Earth, though no humans will likely remain to observe it. More distant galaxies appear proportionally farther back in time. Galaxies 100 million light-years away appear as they were 100 million years ago, when dinosaurs still walked Earth. Galaxies a billion light-years away appear as they were a billion years ago, before complex multicellular life existed on Earth. Galaxies 10 billion light-years away appear as they were 10 billion years ago, when the universe was younger, when galaxy formation was still ongoing, when cosmic conditions were significantly different from today. The most distant galaxies we observe, over 13 billion light-years away, appear as they were shortly after the Big Bang, when the universe was less than a billion years old. These are ancient, primitive galaxies, smaller and less organized than modern galaxies, containing only stars formed from the first generation of enriched material. Many of these distant galaxies no longer exist in the forms we observe them. They've merged with other galaxies, evolved into different structures, or been disrupted by gravitational interactions during the billions of years since the light we're receiving left them. Astronomy, therefore, is archaeology, studying the past through light that has traveled for cosmic ages. Every observation is historical. The night sky is not a snapshot of present reality, but a composite of many different eras, with each visible object appearing from a different moment in history. Nearby stars show the recent past. Distant galaxies show the ancient past. The cosmic microwave background shows the universe as it was 380,000 years after the Big Bang. This means we can study cosmic evolution not by watching single objects change over time, that would take millions or billions of years, but by observing many objects at different distances, seeing them at different cosmic ages, and reconstructing the story of how structures form and evolve. We see galaxies at all stages of development simultaneously. Young, small, irregular galaxies in the distant universe where we look far back in time. Mature, large, organized galaxies nearby where we look at more recent times. As sleep finally takes you, picture the universe not as a static arrangement of objects in space, but as a four-dimensional structure in space-time, every object existing along a timeline from its formation to its current state, with our observations sampling different points along those timelines depending on distance. We see the universe in time as well as space, studying its history through light that preserves information about conditions, when and where it was emitted. This temporal aspect of cosmic distance means that the universe's size is also the universe's age. The observable universe is 93 billion light-years in diameter, because it's 13.8 billion years old and has been expanding. The cosmic horizon exists because there hasn't been time for light from farther regions to reach us. Distance and time intertwine at cosmic scales, becoming inseparable. Every distance is also a duration. Every observation is also a glimpse of history. The numbers that seemed abstract, millions, billions, trillions of light years, now carry temporal meaning. 1 million light years doesn't just mean vast distance, but also means observing conditions from 1 million years ago. 1 billion light years means observing the universe as it was 1 billion years in the past. The numbers quantify not just space, but time. Not just separation, but history. As you rest in darkness, drifting fully into sleep now, consider that the light touching your closed eyelids from distant galaxies is ancient. Photons that have traveled for billions of years across expanding space, carrying information about conditions in the early universe, finally arriving at this moment to be absorbed by your eyes or your bedroom walls, ending journeys that began when the universe was young and will never be repeated, because those exact photons will never travel that exact path again. You exist at one moment in cosmic history, 13.8 billion years after the Big Bang, when the universe has expanded, cooled, structured itself into galaxies and stars and planets, evolved conditions allowing complex chemistry and biology and consciousness. Other moments had different conditions. Earlier times were hotter, denser, more uniform. Later times will be cooler, more expanded, more structured, or more dispersed depending on dark energy's behavior. The universe you observe is not the universe at one time, but the universe across all times visible to you. A composite of different eras, different conditions, different stages of cosmic evolution, all compressed into the night sky, all visible simultaneously because light preserves history, because photons carry information about when and where they originated, because the finite speed of light transforms every observation into time travel. This is the final perspective on cosmic scale. Distance is time, space is history, and every observation is a journey backward through the universe's evolution. The numbers measuring cosmic distances also measure cosmic ages. The vastness of space is also the depth of time. The universe is big because it's old, and it appears as a spread of different ages because light from different distances started traveling at different moments in cosmic history. Rest now in this understanding. The universe is 93 billion light-years across and 13.8 billion years old, and these two measures are intimately related through the finite speed of light and the expansion of space. Every photon is a time capsule, every observation is archaeology, every measurement of distance is also a measurement of history. Sleep peacefully, knowing that the universe is vast in space and time, that you exist at one particular moment in cosmic evolution, that the light you see tonight comes from countless different moments in the past, and that this temporal dimension of cosmic scale makes the universe not just big but deep, layered in time, structured through history, observable across its entire evolution from ancient times to the present, all visible simultaneously through the patient, constant travel of light across expanding space.